Yeah, we'll continue. We'll finish up extrusion like I promised in the morning, and then 3 o'clock, but in an hour or so, we'll finish this. If you have questions, please stop me, ask. We'll do that. And then maybe once I'll take 45 minutes or so to finish this. And then we can do, if you want, both of us are here. If you have questions from anything that we have covered so far, we can do kind of a summary roundup because tomorrow topics will slightly change. We no more rheology then. Tonight, all your concrete will set and harden, and tomorrow morning we'll deal with hardened stuff. Okay. So if you have questions, both of us are here. We can take. All right. So we talked about extrusion, a methodology to characterize extrusion, to link how you measure that extrusion, to link that to what you do with a fundamental rheological characterization that you've done in the lab. And then I showed you some overall ways in which you can create nomograms, you can create control structures for how you print with your pressure, your velocity, and all of that, right? All big picture. Again, everything, like I said, are guidelines, are process documents that you have to refine on your own, taking into account your specific conditions of materials, printer, processes, and all of that. Is that idea good with everybody? Right? So now we'll do a little bit more of what happens to the material as you go through, picking up from the first lecture that you heard from Professor Subramaniam on Tuesday, right? So understanding it better from the point of how do we relate it to pumping. So if you have extrusion that happens, so what I'm showing is half the cross section of a pipe or an extruder. That's only half the cross section. So what you have is very close to the wall of the pipe, you have a lubricating layer that gets set up, right? A paste-rich layer that is closer to the pipe, and particles migrate to the center of the pipe. That's called shear-induced particle migration, a very, very, very well-studied field in fluid mechanics, in particle mechanics. So it's called shear-induced fluid mechanics, shear-induced particle migration. So you have shear flow close to the wall, and you have plug flow as you go away from the wall to the center. So if you have a liquid layer, that's a lubricating layer, right? The shear rate in that liquid layer is the velocity of the liquid layer divided by height of that liquid layer. Correct? Shear rate is the velocity. Remember, shear rate is velocity over distance. We talked about that when we started early rheology, right? So that is your shear rate in the liquid layer. Now, shear rate in the liquid layer and the shear rate in the layer rich in particles is going to be different. Therefore, they are going to be flowing differentially with respect to each other, which means you will have a lubricating layer that's very close to it, which actually is good because it is like you have lubricated the pipe walls with oil so that the things will move very slowly. All of you have demolded concrete from your molds? And have you tried demolding when you did not put in oil when you made your concrete? You forgot to put in oil and then you want to demold. You know the difference, right? So that is a lubricating layer, and that if you have oil, what you get is a plug flow. Right, the whole thing will come out very nicely. If not, you will have lots of shear on the edges. So you will have a liquid layer, and the lubricating layer has much lower Bingham parameters. What are Bingham parameters? Yield stress and plastic viscosity. Both of them will be much lower for the lubricating layer. Why? Because the lubricating layer is a fluid-rich layer with particles having migrated away from it. It's more of particles, right? The particles have, or the fluid itself has lower yield stress and plastic viscosity because the particles have gone away from them. And then if you try to extrude some of those, now, what are the different ways in which you want to extrude? So here are some classic examples. So you want to connect that boundary layer properties with how you want to extrude. This is something called an infinite brick extrusion, where it's actually a very thick fluid. You extrude it like a brick. Basically means It comes in, it's very shape stable, it just stays like that, very stiff mix, right? Infinite brick. You can have a shaped brick where, because of your overburden pressure, you can have some kind of a squeezing. So you have a certain dimension of the nozzle. Here, what you get is exactly the dimension of the nozzle. Here, because you see that it's spreading out a little bit more. Here it's pressure by print head. The print head actually exerts a pressure so that you get consolidation while you print itself. It's not a very efficient method because you really can't control that pressure. And then, of course, spreading by deposition. This is what we normally do, where you exert a little bit of an overburden pressure on the printer if you have to by adjusting the nozzle distance and all of that, but flowable spread by deposition. So the height of the layer, this is one. So somebody asked, how do you calculate the height of the layer, right? So this is one way in which you theoretically calculate the height of the layer. What are the parameters involved? Tau naught. What is that? Yield stress. Rho g, it's the gravity and the density. The thickness of the layer, or whatever is the width of the layer, and 2 over r. R is actually, so this is a circular nozzle. You see that? R is the radius of the nozzle. So based on that, you can, as a function of the radius of the nozzle, for a flowable spread by deposition, you can get some indication of layer. So what you say is that this is proportional to square root of yield stress. You see that? Basically, the height is proportional to square root of yield stress, which means what do you do if you want to have a thicker layer? You want to have a higher or a lower yield stress? Higher yield stress. But then you don't get the entire benefit. It's a square root variation. Correct? So as you make the yield stress higher and higher, you get the square root effect only. So if you make the yield stress higher by 4 times the thickness, you get twice the effect. If you want to get 3 times, you have to make the yield stress go up by 9 times. You see that exponential change? What does that tell you? You will get to a point where dealing with yield stress becomes uncontrollable, right? So if you say that, right, we've been always saying for buildability, better yield stress, for better layer height, better yield stress. Yes, up to a point, beyond that, you're going out of control, right? Oh, I got this layer, I want to have a little more layer. You really want to get your yield stress much higher. Now, what happens if you get your yield stress much higher? Your extrusion pressure that is required is going to be that much higher. What happens if you put in so much of pressure on extrusion? Your filament is going to be not a very consistent filament. It's going to break. You see that? You see all these different things that we have learned coming back again in how you create the dimensions for the layer that you make. So yes, yield stress is an important property. What I want to emphasize is that all of these properties have sweet spots. And in 3D printing, the biggest challenge is to find those sweet spots. And they, based on the material, based on the process, based on what you want. Remember, we had the material, we had the process of printing. Now we are doing the print parameters, the layer height. See how gradually we are getting to the next part of the final printed structure, right? So there, yield stress, there is a certain limit beyond which yield stress is not going to be very helpful. You have to really increase yield stress. That's not going to help because it's a square root function. So make a note of that idea, that height of the layer. Theoretically, it may not work exactly the same way, but generally, that's how it is. Okay, so what happens with your lubrication layer? So when your extrusion thing comes out, you have bulk concrete, you have a lubrication layer. Now, if your lubrication layer is thick enough, what does that mean? Lots of water that was part of your concrete is now stuck in the lubrication layer. What you're getting is a water deficient mix that is coming out. So you need a certain lubrication layer thickness so that things come out nicely, but you don't want it to be too large also. And this lubrication layer will determine whether the shear thinning stuff that you started to put in is coming as shear thinning or will come as Newtonian, right? That will change the behavior also. So we'll see some of those. So here is you apply a pressure, same thing that you saw earlier. You apply a pressure. This is the way the pressure is being acted because that's the shaping that you have to do. But I showed you, for some of you who asked me, I drew this picture. You saw this, right? This is the shaping stress. That's how the material is being shaped. Those are basically the force lines, how the material is being subjected to force. So you have a plug that's anyway going to come in. The rest of it, now it's like a competition. So have you tried to get into a very busy, crowded train? If you go to Bombay, for example, right? When the doors of the train open, who gets preference to go into the train? People right on the door. So if you're slightly here or there, how does that go? You see a flow pattern like this developing, right? You get squeezed in that way. Same thing, you get squeezed in that way. So again, nature also does the same thing. Traffic, have you seen vehicles converge into an exit, from a highway into an exit, out of exit? How does it happen? Through these exact flow lines. Traffic patterns, people patterns, flow of fluids, all governed by the same rule, same law. So when you have a traffic designer designing how to design an exit for a large number of vehicles. So if you're in New York City and you're designing an exit for so many cars and how much the exit side dimensions have to be and how many lanes have to be there in the road that this exit goes into is determined exactly by these flow patterns. The theory is exactly the same. See, transportation and fluid mechanics and materials and people crowding in the railway stations all work in the same mathematical principle. So that's what happens. So here is a pressure. This is what I showed you. So let's look at a little more closely of what we saw earlier. You apply a pressure on your piston. You are pushing this thing through. So you see a shear stress that is in some form because in the center there is really no shear stress, right? It's a plug flow, no shear stress because shear stress is a wall quantity. Shear stress is when you have only a boundary, when you have, remember your parallel plate rheology, you have one plate that is stationary and the other plate is rotating, right? You need one to shear around. Same thing, you need a wall and in the middle you have zero shear stress. And as you come here, that's P1, that's P2. I showed you the equations in the morning, P1 plus P2, how to calculate all of this, right? We know now all of those. And then you get your material coming out like this. See here, the material coming out, you will have a core and a skin. What is that skin made of? Skin is a lubricating layer. So now if you want to take a small piece of this and test the microstructure, this will be more porous, this will be less porous. So you will have a skin and core come like this, and then depending on the shape, you will have your layer shaped like that. Now you see, you put two layers together. Now let's talk about a situation, right? You have one layer that you put like this, and then you put a next layer, right? Now you're worried, why do I have more porosity in the inner layer? You don't know why you have more porosity in the inner layer, correct? Oh, I tried to put it as close as possible. I try to squeeze it. Still, I have more porosity in the inner layer. Yes, you will have more porosity in the inner layer because this is something that you cannot get away with. If that's a shape that it creates. So we will see some of this. Is just a prelude to what we will do tomorrow with respect to microstructure and all of that. All right, slip. Now, what does this lubrication layer do? It helps your bulk of the concrete to slip along the pipe. What is the advantage? Hmm? Lesser pressure, meaning if I'm worried about the work that I'm doing to get this thing out, I'm doing less work. Less work, less energy. Correct? So your extrusion now happens with a lesser energy. You're not unduly over pressurizing. Remember, I told you the effects of over pressurizing when you get out of the nozzle. So your slip layer does that. The velocity of the liquid is zero. You saw this kind of a velocity curve where this is your plug flow. That's your wall slip that's happening here, and there's an apparent slip layer here. I'll show you how to measure this thick layer, all of those. But what happens is that all these particles lock and crowd in place. We're talking about smaller particles, not aggregates here. It's only cement paste. Particles lock in place and then reduce the Brownian motions that disturb the slip layer. So the slip layer is kind of a very nice, unbroken, unaffected part that is very close to the wall of the pipe. So there is a velocity in which that moves through, and there is an apparent slip velocity. We'll see all of that. That's a function of volume fraction of particles. So as you have more and more particles, as your particle density is much more, you will have much easier and nicer plug flow. That's a function of, and that's another reason why your particle packing has to be good. A good particle packing allows you to have a consistent good flow. Um, that's why the importance of microstructural packing. So packing factor, yesterday you saw all of that. The packing factor, which is the coordination number density, and the what was the other thing? Means and centroidal distance. Using all of those to get a packing number, the packing factor, as something to enable printability. Okay. So how do we do this? Again, if you really don't want to know all of this, don't worry about this. But I'll just show you. This is the way you can do the theory for shear stress on the die wall. You remember the shear stress, because this is what is more important for me to let the material come out. After I apply the pressure, this is what I need for the material to come out. So die wall stress is a function of pressure, which is a function of velocity. So we saw all of that, right? Remember, pressure as a function of velocity in the morning. Pressure as a function of velocity, diameter, and the length. That's your shear wall stress. There is something called Bagley correction because there is die entry effect. Things are coming into the die, into the entry, so there is some pressure changes there. There are viscous effects of the material. So you do Bagley correction, you do L plus ND, where N is the x-intercept of the P versus L over D curve for different die lengths and a given die diameter. So you basically do tests on dies that are 10 mm long, 20 mm long, 30 mm long, 40 mm long with the same diameter, right? And you do, that and plot the pressure versus L over D, and where that hits the x-axis is the value N. So you put that L plus ND. So this is called the Bagley correction. We use that. And then we use standard Bernoulli's condition, the velocity that that comes out is the velocity in the piston times barrel divided by die. So it's a ratio, Bernoulli's continuity equation. And then you find out an apparent shear rate, right? So now, remember, this is not, I have now no control over the shear rate, like your laboratory rheology test where I can say, shear it at a shear rate of 5 per second, 10 per second. I have no control over it because I'm not doing shear rate. I'm doing only pressure and velocity. That's what I have the controllables. I'm printing now, right? I'm no more in the lab. I'm in the field. I have pressure and velocity. How do you use pressure and velocity? And this Q is the flow rate. Using flow rate to find the apparent shear rate, which is a function of velocity. You can find that that's your 8V over D. And these are average values for the flow inside the die. Why average values? Because the velocity here and the velocity here are not going to be the same. Correct? Because along the shear wall, particles are not moving, whereas in the middle, it's moving. So average velocities. And then you can say the total flow is a flow that's coming from the bulk plus flow that's coming in the slip layer. There's a little bit of flow in the slip layer, small value. And you can say that velocity is the bulk velocity plus slip velocity. You can do all of that, and you do some calculations. You will find the apparent velocity will equal to the bulk apparent shear rate is a bulk shear rate plus a factor that is wall stress over square of the diameter, and a factor beta, which is slip coefficient. And you can define slip coefficients for different functions. And then how do you do this? So lots of calculations. Again, we have one full paper published on the entire set of calculations, right from how do you do characterize it from all the viscosities and all of that. Here for viscosities, because we needed more parameters, we did not use a standard rheology equation like your Bingham model or Herschel-Buckley. We actually did what's called a Carew model, where it's a viscosity model. It's a viscosity as a function of of your ultimate viscosity plus some average viscosities and all of that, and shear rate. Viscosity as a function of shear rate. So you get the what's called the flow index from this model, and then you get the true viscosity is bulk velocity. So that's your slip layer. If it's a Newtonian fluid, that is your distribution. Whereas if it is your non-Newtonian fluid, you have a bulk shear zone, and then there's a plug flow zone. Remember the velocities day before yesterday? You saw this picture. So your shear stress, slip velocity, and viscosity of particle repeated load, you can calculate all of that. And here is some examples. See the velocity here. So here is the observed apparent velocity. So this is your die. 0 is the middle and -2 to +2. So that's a 4 millimeter size die that you have. You're extruding it to. So for a certain pace, we'll show you different pace here. So this is OPC. That is your observed apparent velocity. That's your true velocity. And that's a slip velocity. See, slip velocity is fairly constant because at that slip zone, and it's going to be lower than the apparent true velocity for a 4 diameter capillary. These are for OPC. This is for a limestone mix. This is when you have a superplasticizer. See what happens here? The behavior completely changes, right? So your apparent velocity that you observe, can you see the difference in shape of this curve correspond to these two, the velocity curves? So this is the velocity in the middle, right? That's at 0 is the center of the pipe. So what's the velocity there? About 12 millimeters per second. If I have a mix that's superplasticized, that velocity drops down slightly. Because why? It's able to flow much better. But what is more important is to see how the velocity starts to develop along the edges. So you have a sharp profile of velocity that is changing, whereas your velocity is almost constant. See that here? Which is an indication of the uniformity of the material. Because of the superplasticizer, you have separated the particles nicely, you've spread the particles away, the layer, the slip layer is very nicely organized, and the particles in the bulk zone are very uniformly distributed. There is not much of gradient in the slip zone. So you'll see that it's quickly transitioning into its velocity quickly here. And this is for your velocities. Now, if you look at the shear rates and the true velocities here, and I want you to be carefully looking at here. This is for OPC. This is for a mix with superplasticizer. You see the change here, right? This is a Newtonian fluid. This is a Newtonian behavior with a sharp um, velocity at the middle and gradually increasing. Whereas for all of this, you will see some kind of a plateau. So when you get into a superplasticized mixed, you get closer and closer to a Newtonian fluid when you get to an extrusion, which is what it is. Superplasticizers will make you go closer to a Newtonian behavior. So you can find out your shear rates. So now what we're doing is what this will tell you is if I know the shear rates that my printing process is actually subjecting me to, can I now take this mix into the lab and characterize it at that shear rate? Now you have one more correspondence between what your lab measurement and your field measurement is. You can say, I know my flow through this extruder using this calculation has an apparent shear rate of that. What is now my yield stress? What are now my parameters at that shear rate when I measure in the lab? So it gives you one more place to evaluate, but also helps you to understand how the flow patterns change with different types of material under the same extrusion conditions, same conditions of processes in the field. So one more thing to think about. And finally, the idea of buildability. Yes. Why should that be? So slip velocity is much higher for a superplastic mixed. Why? You tell me why. You've been working on this. So this is the slip velocity, right? This is the true velocity. In the middle of the pipe, it's a plug flow. Which one? The blue one is the true velocity. This is shear rate. Yeah, this is the true velocity. Correct. True velocity here. No, what are you asking? Hmm. Yeah, correct. This is the true velocity. Yes. Both will look same. Yeah, it could be different. I don't know. I have to look at what the paper is. But these are in this you actually has a viscosity also. I want to show the viscosity differences too. Right, viscosity showing like this probably could be different mix. I don't know if I have to look at the paper to see what it is. But you see here, in this case, you see the slip velocity. I'm not showing the slip velocity any of those here. It is only the true velocity that I'm showing here. But I have to look at what the difference are. They might be different mixes. This is I don't know. I'll have to look at it. But you get the general trend. I know you should look at the paper. You should know this. You should not ask me these questions. You should know this, right? You've been working in this area. So this is your viscosity. When you have viscosity that is having this shape and having a sharp value in the center, this is your Newtonian fluid. Whereas these are all non-Newtonian. So with superplasticizer, it behaves. That's what I want to show. Can you go and look at the paper right now? While you're sitting there, and since you asked the question, go look at this paper and tell me what that is. That's the ACI paper and Suraj's 2021 paper. All right. So we'll go onto buildability now. So far, we have extruded it. We have a layer that's out there. Now, what do we want? We want to build it up so that we all can go home. Right? So buildability. What is buildability? We talked about this yesterday. That you have structure formation, you have the yield stresses that's coming in. You want this blue line to be always above those steps so that your structure is stable. So this is your yield stress, and then that's your time or number of layers, and all the stresses and all of that. So this is a rope coiling, the one I showed you. If you just do this, actually a snipper from a video, but you see with different um, uh, cement to superplasticizer ratios, you see how much buildability is being changed. Okay. So the several buildability challenges, if you're building only very straight up, fairly straightforward. Buildability will become a problem if you're doing curved structures, if you're having overhangs and things like that, then you'll have to be very careful. Slow and difficult to control stiffness evolution impedes layer-wise concrete printing. So what is important in buildability is actually stiffness development, right? And that's why I told you yesterday that yes, yield stress is important. And I actually showed you now why increasing yield stress indefinitely may be difficult with respect to layer heights as well. You have to go really, really small heights otherwise. So stiffness calculation becomes a much better way of doing it. So slow fluid to solid transition restricts printing speed and height and maximum possible overhang and limits the printable geometries. So you need some active rheology control. There are ways to do magnetorheology, microwave assisted heating. I'll show you some videos where we've actually done some overhangs by having a heater at one end of the small scale structures that we have done, which you can actually do large scale structures too if you have a heater that comes in, but we did polymer because to deal with cement paste and a heater on it, who will worry about shrinkage and cracking then, right? So there are ways in which you can do that. So how much can you do overhangs, how much you cannot do, how do we find the ways to change all of this are all structural scale challenges. Remember, right, 3D printing will get its maximum benefit if you are able to do shape optimization geometry. If you're simply doing rectangular structures, this really doesn't add value. Adding value comes from, like in the very first lecture you heard, customization. You're able to customize things in a different way. So if you really want to have overhangs and stuff, that becomes a problem. So here is an adaptive layer thickness printing. This is what I told you. Um, see, hopefully. Yeah, you'll see. So printer printing and then a heater giving heat instantaneously um, to suppose so a dome structure. It's being printing a dome structure. So you can see lots of overhangs. You see how the shape changes, right? So to ensure buildability of this, you need both rheological control as well as, again, it's a very small scale structure, but thinking about doing it in the large scale, you need a way to have heating as well. Here, layer thickness is varied from 3 mm to 1 mm from the bottom to the top of the dome so that you have much better control. Why is that so? Why did I change the layer height? Yes, correct, to do it, but what effectively changes? What did I show you earlier? Layer height is related to square root of yield stress, right? So now if I'm heating it, I'm doing a heating immediately. I have now control over yield stress also, and overhang is taken care of. You see how the thing is building up like this here. All right, we'll. It's a polymeric material. It's actually, well, it is cementitious, but it has quite a bit of polymeric content too. So it has enough of give within it because of the polymeric material that cracking, it'll automatically take care of it because you have lots of polymeric, small amounts of polymer, but it can take care of it. Okay, so we'll talk about a model for buildability that we have developed. It's Avina's part of his PhD work, where we looked at material property development, stepwise stress growth using printing and failure modes. What we have done here is to simplify the process so much that you can use very simple mechanics models to predict buildability. I don't want to use fancy models, don't want to deal with the material changing so much, to see what simple modes of failure are available, and then can we use some non-destructive quick way to predict that as well. So here is a very, very basic idea, right? Stress growth in layers. So as I print more and more layers, this layer that I've printed is going to get more and more stresses, correct? So on layer 1, this is your first layer. Initially, that's layer 1. When the first second layer is constructed, that much of stress. When third layer is constructed, that much. When fourth layer is constructed, that much. When 11 layers or 12 layers are constructed, that is a stress on layer 1, correct? And stepwise, can I not find the stresses on all of these layers? Very simple. Requires no calculation. All you need is weight of the layer that is being built up. That's all you need to do that. So that is your stress growth in layers. Um, so for that you need rho, g, and h. Correct? That's your weight and the height that you're building up. Now, material characteristics will show you what material characteristics are that you need for this and what are the failure modes. So now you can come up with so many different modes of failure. Let's simplify it. There will be an elastic buckling. As I keep layering more and more and more, I will have the tendency to have buckling of it. So I can have elastic buckling. If everything is under an elastic load, it's elastic buckling. If I'll talk about what plastic is, if there is plastic loading also, or you have crossed the elastic limit, you can have elastoplastic buckling. Very similar idea. You can have plastic crippling, and then you have plastic yield. Basically, it is just yielding from the bottom, like spreading out and not being stable. So those are the four models, that four modes of failure that we considered, and then there is the theory for it. So stress per layer is filament weight over filament area. You can say rho Hg. That's where you have here. Okay. So what we did for stress growth is, so here is what we want. We want to find out the material properties, right? So what we did was to take the material, take print. How many layers did you print? 4 layers? To 6 layers. So to print 6 layers, and very, very carefully using a very sharp pipe, cylindrical pipe, slowly push through the material to extract a cylinder from that printed material. And then do a very, very, very slow loading of that material, extremely slow loading of the material. And there is soft material theory that shows that if you really load a material very, very slow, now that is how you are going to be building up, right? It's going to be very slow loading, depending on your printing rate, but generally it's going to be very slow loading. So in that very slow loading, there are theories that say that your stress strain response, even at very early ages, is a bilinear response. So if you can really do it, and he claims that he can do it, right? He claims that he can really capture the bilinear response. If you load it really slow, you can get a bilinear stress strain response. You call this first slope the elastic response, and this we call it the plastic response, just for a lack of a better word. That's still very early. So you call a plastic modulus and an elastic modulus, plastic stress and an elastic stress. So you have an elastic regime very early, a linear plastic regime, and then it becomes completely non-linear. If you look at the stress strain curve under compression for this little cylinder that you have extracted from a printed specimen. Why do we need it? These are the actual material characteristics that you need, right? For any model, you need material properties. And material properties are basically the elastic modulus that we want for this. So what happens with printing progress with time? If at some time I have printed 3 layers, the first layer has only load of 2 layers above it, correct? Which means they're probably all within this range, which means it's all elastic. You see that? And at some level, I get to this point. I get my bottom layer to be stressed to that point. So you get your elastic limit. And then beyond that, what happens? While these layers are all under elastic stress, because this layer has only the load of 4 above, whereas these guys have the load of all 7 or 8 above, correct? So they have gone to this range. You see that? And with time, you are going to get more and more into the plastic layer. So layers experiencing stresses lower than the elastic yield stress are this, and the sigma is a stress on the bottommost layer. So what that stress is, this is how your print progress with time. This is what the layers are experiencing. So if you are able to put in a strain gauge on each of those layers, or some way to measure stress on each of those layers and look at what is happening with time, this is generally what these layers are experiencing. Okay, so we use that idea. And then we use very simple failure modes. These are all standard failure modes that you can get in a mechanics book. That is your uh, plastic height, that's your crippling length, so crippling height, that is your, what's that, buckling? Effective buckling height, right? That's a buckling effective height, that's elastic buckling. So all of that, you use all these simple equations that you have, and then you see all of those. So you, from your experimental part, you find the material strength, you find the green compressive strength, all the elastic modulus, all of this, you can do it. Theoretically, all these equations, you can get your elastic self-weight, elastoplastic self-weight, plastic crippling, plastic yield, all of that, and then see the theoretical failure height for each of those versus your actual height that you can print, and see which mode works. So theoretical failure height is equal to experimental failure height. That's your failure criteria. And then you do green compression test at strain rates. That's what showed earlier. Print um, different geometry specimens for walls, all of that. So for different specimens with 30% of limestone, 30% of limestone with superplasticizer, with 20% fly ash, 10% limestone, 30% of limestone with a lightweight aggregate. You can do all of that you can find the yield stress modulus, elastic and plastic based on these curves. These are your material properties. So you need this to make the prediction. Again, the idea is a priori, ahead of time, predict given a mix, how high can I go? Right? Given again, all of this based on a given printer, given conditions of extrusion, all of that, right? If that changes, some of this will change, but general idea of how that happens. And then you can do the yield stress growth. Remember the same thing with the thixotropic coefficient, plastic yield stress as a function of time. You can do the same. That's a plastic yield stress. Right? This value. Now, this is not a rheological yield stress. This is a yield stress from a compression experiment, from a green compression, from a fresh state compression experiment. It's a yield stress from a compression. So not a rheological yield stress. But you can do the same thing as you do the rheology. You can still get a thixotropic coefficient from this. You can still get a structuration rate build-up coefficient from this to see that for that material under these conditions, what those values are. Instead of using a rheological parameter, I'm using a compression parameter simply because in the build-up phase, I'm not interested in shearing. I'm interested in axial loads being applied like a compression test. You see the correlation? Theory remains the same. Nothing has changed. Fundamentals remain the same. Instead of a rotational yield stress, now I'm simply looking at a compressional yield stress and using the layer buildup rate because that buildup is now a function of how much it is gaining strength as a function of time when I build up those layers. So you have the same way that you can develop this thixotropic coefficients, and then the model verifications using walls and this. So basically what you have is all these green dotted line are the experimental values of how much time, how much height you could build up at different times, right? Very early with time, after 1.5 hours, how much could you build up? This was the experimental one, and whichever curve, theoretical curve, here, for example, is the plastic height that is following it, right? So it's a plastic failure. You can follow that. So in each of those cases, there are different modes of failure that will happen. You can predict your buildability based on um, where your experimental value and which theoretical failure mode matches it. Different specimens, different conditions, different times, you will have different failure modes. So how high? This is again some printing with graphene. Calculated failure height from the models was for this control 1 hour, 1.5 hours was 31.6. Experimental height was 28.5. For this one was 54.8 calculated. Experimental was 49.5. So fairly close. You're able to predict how high you can print based on very simple models. So a priori, you can have estimations of buildability, right? So that's one way of doing it. Now, okay, I don't have it. If I'm actually building up stuff, can you tell me while I'm building, will I fail or not? Yes, you can. More expensive, more time consuming, more sophisticated. You can do digital image correlation. So that's what we have done here. So you see, these are 4 layers that have been printed. And again, very fresh concrete. You have to speckle paint. So digital image correlation is basically you're taking images of the cross section and then you speckle paint on that, and with time as the points move because of deformation, you track the movement of those points and find the strain that is built up. So that's what digital image correlation does. So basically the surface measurement. So you don't ask me what is the internal strain same as the external strain. We would like to think all of those strains are the same. They're essentially not, but at least you can get the surface measure. And in places where you can't go and put in a strain gauge right inside the material, it's a very good approximation. So you're getting on the surface. So you can your concrete surface, your wet concrete surface is very dark, right? So you need to have some bright speckles to give you contrast to see how the points move. So we have some white paints. I think it was a little involved process of doing this. I think you can talk to Abhinaya to figure out how he managed this. But you can speckle this and get it, and then you can see which with each subsequent layer that's being built up, see, the darker the color gets, the higher the larger the strain is, right? So much higher strain in the lower layer, much lower strain in the top layer, as you would expect. And I'll show you in a later picture when the nozzle gets there, you see that strain as well. So now look at this. This is printing time. And here is the vertical strain that is being measured by DIC. See, so 4 layers have been built and you're going to paint this. Now I'm going to print layers 5, 6, 7 on top of it. So 4 layers have been built and I'm going to watch. I think this is all layer, seeing whatever is going to happen in layer 2. So I'm going to find out what is the strains. When the layer 5 is being printed, you got the strain. Your nozzle is now moving to the next one. So you lift the nozzle a little bit. You see that strain dropping slightly, right? And then the nozzle comes back and pushes more load. One layer is done. The nozzle lifts up. So the strain is released. Then you put again. So again, different layers are being printed. And I think this is on layer 2 when all this stuff on layer 1 actually. Strain profile of layer 1 when layers 5, 6, and 7 are printed. Now this, if you have a very sharp eye, would you mind me telling you that this is no different from this? Would you be okay with me saying that what you saw there is this, well, this level of change, correct? So whatever I theoretically determined to be the vertical force is actually, there it was stress, here it is strain, is pretty much a vertical strain. So now I can actually find out what the vertical strains are while are being printed. And then here is the vertical displacement. So this is where during printing resumed after speckling. So you'll see this strain here. That's because the nozzle is right there. So this is all being printed. And this one is 3 more additional layers have been printed on top of 4. So you can see the strain in these layers. Now you see that before failure is initiated, you see that in this area, higher strains have been detected. Much higher strains detected in this area before failure. This is a critical failure when right end of the print falls. You can see that. And then this is for the lightweight motor. So you can actually see, if you look at very closely here, you can see the print failing here, crippling near the interface of 5th and 6th layers. You can see here all of that. Vertical displacement. You can also measure the out of plane displacement. Why is out of plane displacement important for me? Buckling, right? Buckling is out of plane. So now I can find the out of plane strains and you can find out if it's going to be the out of plane strains, if it's going to be buckling, that's dominant. I can look at vertical displacement to see if it's yielding, that's dominant. I can look at out of plane displacements, out of plane strains to see if buckling is dominant. So you can do all of that, and then you can even go a little bit more if you want to do the analysis to look at the slopes of how the strain rate changes. Positive slope versus negative slope in strain rate. Negative slope is you're going away from your plane of viewing, buckling, correct? Positive slope, when you're doing the building up, it is yielding here. So again, that's another way to figure out if it's buckling failure or yielding failure. Ways in which you can more sophisticatedly do this and predict what will happen. Again, not recommended for field printing because this DIC instrument is expensive to put it, to calibrate it. But what will a certain mix do in the lab? You can get good indications of what its behavior will be. So that's the strain time relations and all of that. So you can do critical and initiation heights. The other thing with this prediction model is even before it fails, you can predict the initiation height. And therefore, if you actually are doing it, if there is a way to simplify this and do this in the field, you can stop printing if you feel that it's going to actually fail, right? So it gives you a little more warning before failure if you can do it. Again, currently it's all a nice framework. How do you implement in the field is a big question. We don't know yet, but if somebody could have a cheaper DIC system that they could develop, even if it's of a lower resolution, potentially a way to understand how to do this in the field. Again, we can look at what lightweight mixtures do. Like I said, we have to do lightweight mixtures to reduce the weight so that we can make modular structures and carry it in a truck. So lightweight is important. You can find the rate of stiffness increase. You can see how the stiffness is increasing with time using these values. Um, you can see how the buildability changes with time. You can do all of that. You can create failure envelopes, a crippling envelope, plastic collapse envelope, failure initiation. You can do all of that. You can see what is your approximate failure height prediction. Some cases will be very close. Some cases you will have much bigger spread in the prediction. But and again, a methodology that is good for lots of laboratory work to understand how different mixes are buildable. So one way of evaluating buildability, like I showed you, is using these models and the validation with experiments. I think that is pretty much what I have with buildability. So we have gone the entire way from laboratory parts all the way to printing it, printing layers, building them up. Now they'll have to harden for us to do the next lecture. We should give it time, so we'll do that. Tomorrow, we have some time now. We have 10, 15 minutes. So both of us are here. If you have any questions from any of the stuff that, again, I hope that you're able to track the process from taking a mix and characterizing it right from the lab to taking it all the way, printing it, building it, and walking the entire process along with it, right? So again, all the notes, if you look through the notes for maybe 8 or 9 lecture notes that you have now, you will see that progression from basic materials all the way to putting them down and printing it. And if you have questions, please go through them. Please ask. I'm happy to answer whatever we know. Did you guys find out what the answer is? You found out, right? Good. Okay. Any other questions?
It's possible that while extrusion from the average logic, we may be extending the dead zone after, because in the dead zone we have two regions. One is the central region and another.
Correct. Correct.
So if the properties are same, then the central region will always find a way to go. But there must be something to the corner region that will overpower the central.
Correct. So what is the difference between the test setup that you're talking about, the dead zone, and the one that you're actually printing? In the one that you're actually printing, you're constantly putting in material, right? You're constantly putting in, you're not creating a stagnant dead zone at all. You're constantly putting in the material, you're constantly pumping in, you're constantly driving the material out. So whatever dead zone forms stays there as it is. The material will find a way to go around it, depending on the pressure and all the other characteristics that we talked about. So while it is important to characterize which mix might be better for me, when you start to print, it's not a big deal because whatever it is, it's going to stay. You're going to keep on putting material in. Correct? Other questions? That side has been very quiet. Maybe I should move to that side and talk from there, maybe.
It's also possible that while we do this, we can keep real life. Then we be giving some sport, electoral sports, like on a form of.
Yeah, you can do that. Correct. Especially when you have overhangs, you do supports and then print on the supports and remove the supports later.
Then this buckling equations.
No. The buckling equation is for building up layers from ground, right? Yeah. So that is overhangs and supports are different. When you're building up something like this, support means a formwork. The whole idea of doing this is not to do with formwork. What's the whole point of putting a support on this if you're doing 3D printing, right?
That's it. So, Even if we are doing this, we'll have the adjust and the pressure will in its own way.
Yes, that's what I said, right? The dead zone, the reason why you create that kind of a system was to artificially introduce differences between different mixers that you can test and qualify them. If I did not have that, and if I had an angular one, I will not be able to find the pressure displacement differences between different types of mixers. They all will flow very nicely. I will get very same curves, and I will be looking at the same curves and not knowing what the difference is. So this is an artificial difference that I created just so that I can now differentiate A and B. It is, that's why I said it is not something that you will find in the field, but the difference that you have in qualifying a mix is much higher if you create that construction. And that is why, because I created a constriction, is why I had to go in and create a geometric factor to see what those differences are. Right? So, yeah, this is created to understand the process better. It is really not required. But then without that, I have no way to quantify how differently things behave. All right. I think it's been 2.5 days of lots of stuff. But I think you guys should, if you're interested in this topic, if you're doing research in this topic, if you're generally working in this area, um, there's lots of information out there. If you read these notes, I think you will get motivated to go out and look for more. There are plenty of papers. Rheology is a very mature field, not in cement and concrete. Well, cement and concrete also it's mature now, but in lots of other fluids, this is like, this is what they live on. And it is a field where if you have interest in mechanics, this is a field where you can go and have lots of fun. So it's really nice. But we do lots of solid mechanics all the time, and to deal with things that are moving, it's really exciting. And eventually, when you're dealing with something like 3D printing, even with concrete pumping, there is lots of exciting stuff that you can do. The entire field of concrete chemical admixtures off to the field of rheology for them to actually live and survive, right? It's the rheology that they are controlling by adding all of those different things. So very wide topic. If you need more notes, more reading material on anything specific, let me know. Let both of us know. Happy to share with you whatever we have. Happy to point you in the directions that we know might be of use as well.
Now, I'll just add to that. And that is, if you look at the rheology, the first time we felt cement and concrete industry that we need to understand